Hello, my name is Professor Allen Hoffman. I'm in the Mechanical Engineering Department at Worcester Polytechnic Institute in Worcester, Massachusetts. This short video will explain the basic laws of dynamics. Dynamics originated with Newton. In 1687, he proposed his three laws. The first law defined the state where a particle was in equilibrium and stated that the sum of the forces acting on a particle must equal zero. His second law really formed the basis for dynamics. And what Newton said is, for a particle, which is a concurrent force system, the sum of the forces acting on the particle equals the mass times the acceleration of that particle mass. His third law was essentially the law of action and reaction, and defined how we develop free body diagrams. Now, since Newton lived before the time of calculus, he was unable at that time to propose to extend his laws to cases where the mass of an object is distributed in space, essentially a rigid body that has a center of mass. That development of dynamics had to await almost a century, around a century, before it was developed. So this video will deal with rigid body dynamics, where we have mass distributed in space. And that was developed, in order to develop that, it was necessary that calculus be invented. So I always point out to my students, dynamics would have been a lot easier before calculus, but that was more than 300 years ago. Now, there are three basic approaches for rigid body dynamics, all derived from essentially, all based upon Newton's original laws. These three approaches are applicable to different situations, or most applicable to different situations, depending upon the variables that are defined and or known. These three approaches are the equations of motion approach, the work energy approach, and the impulse momentum approach. The equations of motion approach is based essentially on Newton's original law. Essentially is based upon F equals ma, and it represents the extension of Newton's original law to rigid bodies. So in this case, and I'll speak only in I'll speak only about two-dimensional problems, we have a vector equation which says the sum of the forces acting on a body equals the mass times the acceleration of the center of mass of that body. So in two dimensions, you would have an equation in the x direction and an equation in the y direction. In addition, we have the sum of the moments about the center of mass equals the mass moment of inertia times the angular acceleration. And that equation in two dimensions would be in the z direction, essentially our moment equation. So since we have, in two dimensions, we have three scalar equations, we can at most solve for three unknowns when we draw a free body diagram of an individual rigid body. The variables are forces and moments, accelerations, including the acceleration of the center of mass of the rigid body, as well as its angular acceleration. Since accelerations are instantaneous variables, this approach is useful in doing an instantaneous analysis of a single rigid body. Now, the work-energy equations, a second approach that's presented in basic dynamics, results from integrating the equations of motion with respect to displacement. This results in a single scalar equation that states work, which is a scalar, is equal to the change in kinetic energy. And here work is defined as the integral of f dot dr, where dr is the displacement of the center of mass of the body, and plus the integral of the moment times dotted with the angular displacement of the body. The kinetic energy for a rigid body is defined as 1/2 times the mass times the velocity of the center of mass squared, plus 1/2 times the moment of inertia about the center of mass of the body times the angular velocity squared. For conservative systems, that is where the work is only done by conservative forces, usually gravity and or springs, we can represent the work done as the change in potential energy, and energy of the system is conserved, and therefore we get the common kinetic plus potential energy in state 1 is equal to kinetic plus potential energy in state 2. Now once again, this is a scalar equation, so we can only solve for one unknown. It has the advantage that we can deal with systems of connected bodies, and the variables are forces and moments, velocities, specifically the velocity of center of mass of the bodies, plus their angular velocities, and displacements. The third approach, impulse momentum approach, results from integrating Newton's laws for a rigid body with respect to time. So that, therefore, the equations are vector in nature, since the equations of motion are a vector set of equations. And they state that, and there are two equations, in much the same way that there are two equations in the equations of motion approach, a force equation and a moment equation, and vector equations. And so these equations state that the linear impulse, which is defined as the integral of integral of force over time, is equal to the change in linear momentum of the center of the body, which is defined as m times the velocity of the center of mass. And the moment equation becomes the angular impulse equals the change in angular momentum, where angular impulse is defined as the integral of m moment over time, and angular momentum is defined as the moment of inertia of the body about its center of mass times the angular velocity of the body. Now, in this case, there are three equations, and therefore we can solve for at most three unknowns. The variables are vector quantities force and moment, scalar quantity time, and the vector quantities velocity of the center of mass of the body as well as its angular velocity. Now, the impulse momentum equations are very useful and the best method for dealing with collisions, because in the case of a collision, you really don't know the force or moment that is exerted on a body, but you are able to know or measure the changes in linear momentum and angular momentum. If we review the three approaches, we will find that each approach is best suited to solving a particular kind of dynamics problem, depending upon the variables that you know. And the other methods, the other two methods, they often, except for collisions, can also be used to solve any particular dynamics problems. However, choosing the most appropriate solution method will make solving the problem much easier. This concludes the video. Thank you for watching.